Fortunately,
Is
Will.
called Moleskin, yes.
One, yeah, somebody called, yeah, there's something else like that. And there's another one, some kind of tape. They said it's really effective. They did some testing, with 100 some people from Stanford University Medical School. They have them with one foot wear it, another one without, and make them walk like a week. And then found out the one they wore the tape, nobody developed blisters. So that was pretty amazing. So I'm getting that, and I'm gonna have to finish this thing one day. And also the people started early, like people start like at 5:30, I think, and I started like at 7. I thought it was early because I was pretty confident I was able to finish within 10 hours. It's about 32 miles, but it went really bad. But it was a beautiful day. It's really nice. And as the color start to change, the flowers, foliage. So it's nice.
Oh yeah,
So, what?
it's a nice time of year. It's a little warm even.
Yeah, it's a little warm, but I think next month it will be better because the foliage will be all come full blown. So I will do it again. I was thinking, do it every once a month until running out of daylight. I will see. Yeah, this time I spent quite a bit of time find the trails. That was sometime part of it was difficult, so it took me some time, but eventually I was able to map out everything. So it's pretty good. I enjoyed it. So when I was hiking, so I came up with this idea to do a project. I don't know if you had a chance to read the description for the project. Okay. I think it should work out well for our course. I think it's more useful at this stage to have actual complete applications because you graduated from those early 148, 218, like assignments, small questions, rather you're at the stage that you should be able to do the whole thing. Okay, develop the whole thing, a complete program. So there's a few things I think it's good to know, right? One thing that's a main goal of this course is about designing the application. Okay, so that's why when I gave you the description, I think it was a Saturday, when I wrote the description, I emphasized that don't try to develop a coherent project yet. Okay, don't try to sit down and start coding right away. Okay, instead, put some time to think about how to design the program, right? So I said, don't code, just take each type of data and think about how you're going to store the data. Okay, so that ends up, a good time to do it because we just finished most part of the data structure stuff review, right? So this is a time you can put the knowledge into use. So I came up with some data sets, right? The data types, I mean. So one is the user profiles, right? So if you have application, every user should have a profile on the application. So this way you can log in, you can keep a history, identify yourself, right? And then you can have some customization later on if you want to. So I think that is a very common type of data, user profile. And then I thought maybe it's a good time to throw in data about pictures, right? Because when you hike, people take pictures. They would like to store, then they can go back and review, right? And also there is it's a good time to introduce like a user profile picture, right? So initially, since we didn't do much in the past about the pictures, so I think maybe a good time to get into that. Now, I just want to tell you, it's not really something new, right? All you're doing when you deal with the picture is a file name, okay? Because each picture has a file name, and you just have to remember where the file is, like the folder path where all the picture is, and Java will be able um, to go to the folder and open the picture files, okay, using built-in APIs to display pictures, like images, so on and so forth, right? So it seems like a new thing, but it's really not. It's just open the file, okay? Just identify the file in a location. And when you take pictures, it's the same thing. The picture will be saved into a location, and later on you can pull them up, right? And you may notice whenever on your phone, the phone, when you take a picture, your phone loads a picture from, say, the album or whatever. The picture names are very it's made of a bunch of random characters almost, right? You notice it? It doesn't make any sense. The file names, the picture name is just a bunch of letters, numbers, and pretty long for the most part. But it does tell you the data type, right? Maybe JPEG, maybe maybe some other type, but mostly JPEG. So that's why, because they want the picture. Every picture has a unique name. That's all that matters, right? Because later on you're gonna have to load the picture. It has to be a unique one, right? So that's why they make a random combination of letters and numbers to make up a picture. Okay, so that's really the gist of it when you deal with the pictures, right? So when you try to store a picture, you don't really store the picture per se. Instead, you just store the string, right? A string that is the picture file name or the location, right? You may identify the whole path, like a C drive and column backslash document or users document and the pictures. You can do the whole thing, or just keep it in the project folder, and you can just have a folder called pictures, and then behind that you just put all the pictures. So it's really, when you store a picture or retrieve a picture, you don't really store the picture per se. You just store the name of the photo files, or the name of the photo file, right? That's all you do. And you just want to make sure when you store the photo, and the photo name should be a random, unique name, right? So that's why they make it so long, because when you make it long, the chances a random name will be unique, right? Right. If you make it very short, then there's a possibility you have a duplicate. But when very long, it's very hard to have a duplicate. So that's the reason you see a picture when you download a picture. Usually the picture name is very long and complicated. It makes no sense. That's why it's meant to be unique. That's all. Okay, so that's one type of data, right? So I made it kind of simple because all I asked for is a username, right? Because you need to log in, and you need a password as well to identify you, right? Now, usernames are supposed to be all unique. Okay, so you may want the user to create their own username, um, but you won't accept the duplicate username. Like you go to Gmail, try to create an account. If the name is in use, then you can't really use it, right? You have to come up with a unique one. So that's the first piece of data: username, and then password, obviously. Password does not have to be unique, okay? But you may impose some conditions, like it has to be 8 characters or 5 characters. It has to have letters, numbers. Some even require some punctuation, right? Certain punctuations even. So that's up to you. Okay, it's your call now. You're gonna design the application. So that's username, password. Then I kind of throw in a user profile, right? The picture, I mean. So really just a name of a file name, okay, which is a photo file name. And the third one I want to have for each user account is a history. Okay, so whatever trails the user did in the past will be stored. So it itself is a data. It needs a data structure, right? So now you understand. is really we're gonna have a data structure holding all the user accounts, and for each user, you have a separate data structure to store the history of all the trails, also the time, the dates, okay, the person complete that the trail, and the trail name, right? And also, the land, the the elevation gain. I don't know if you know what that is, right? Elevation gain. So basically tells you a little bit about that hiking experience, right? So I want you to keep the order, right? So this way you can go back in time and then look at the order when you did which. So the date and time is important there. Oh, also, I think, no, this is another one. So I think in my classes, I didn't emphasize too much in the past about date and the time. That has a very good Java API for that. So I would like you to take a look into that. So every time you did a trail, did a hike, you're gonna have to store the date and time. I don't want you create your own, date and time, right? So it's gonna be the date and time by using the Java API. Okay. Java API had a few classes dealing with date and time, and so some are outdated already. Some are they call is no longer supporting it. So you may look at the new ones, and also to come with it, Java FX has a date picker. Okay, so now you can combine that, because any kind of application you do in the future, you probably has a date component to it, right? So I think it's a good time you know, to integrate that into application. Okay, just for fun. All right. So the only requirement about the history is you want to keep the order. Okay, you don't want to randomize that. Okay, so people can look back and look at the date in the order they did the hiking, right? So now we need a two data structures at least, right? One stores the user profiles, another one stores the history for each account, right? You got it? Yeah. So I said that at least two because you're going to see later that maybe sometimes you need more than one data structure for one set of data. Okay. So we're going to talk about that later. Okay. Another set of data types we have are the trails. Okay, the trails. I gave a bunch of variables like the name of the trail, right? And then you also give it the length, like how long it is, right? And also the information about the address of the trail. Okay, I said the trailhead address, and also the type, because the trail is just a loop, which is pretty common, right? So you can park your car and then you take a loop, you come back to where your car is, right? So that's common. And then there's another type, it's called point to point. Okay, point to point. So like what I did was a point to point. So I started at Hackshire State Park. So I started from there. That's the South Shore, and supposed to end at Sunken Meadow, which is North Shore. Right? That's point to point. Okay, that's one type, and different from the loop. So I needed two cars. One car, dropped off at the destination first. Okay, then drive another car to get to the starting point. So then afterwards, the two people have to go get the car. Anyway, so there's a second type. Another one is two and back. I think it's called two and back. So it's like a double, all right? So it's not a loop, but you go there and you come back. So basically, if it's a 4 mile hike, becomes 8 miles because you double it, right? So that's another type. There's a couple other things I think I don't remember exactly. I think it's the elevation gains there. Okay, so that is the trail, right? Now I wanted to have certain functions, certain things you have to be able to do with the trails. One is you allow people to search for trails by providing trail words in the trail names. Okay, so if you type one word, then all the trails that contain that word will be returned, show up on your GUI eventually, right? So then you can pick the right one, the one you want to do, right? And as you type in more words, then obviously more trails will be eliminated, right? So eventually, you will get fewer and fewer trails returned as you type more words. So that is one thing you need to implement. Another thing is you should be able to allow the user to kind of return trails based on certain criteria. For example, the length. So if say I just feel like today I want to do 5 miles, right? Then you can just search 5 miles. That's the maximum length. Then whatever mile trails under 5 miles will be returned. Okay, and if you want to do a 20, enter 20, then so on and so forth, right? So you get the idea, and also you can decide the type. I just one person. I either want to do a two and back, or I want to do a loop. So you allow people to search based on the criteria. So that's trails, and then there's another part which is something we didn't do in our data structure course, but I thought it's very, very interesting. It has to do with the graphs. Okay, since now we do have some time, so I may um, give you the chance if you are interested to incorporate that idea into the application. Now, that is about all the stops, intersections I want you to incorporate. Okay, say so you want to hike from here to not hike from here. Say I want to just give you the example I gave you before, hike from Hampshire to Sunken Meadow, right? In fact, you're going to go through a lot of stops, right? A lot of intersections, because there are also a lot of local trails in that area. So basically, you can potentially have different make your own trails. Really, you can combine different trails and make your own path. Do you understand that? Can you see that? It's like when you drive from here to um, say to Washington D.C. or to New Jersey, you can potentially take a different route, right? And depending on the traffic, depending on kind of vehicles you drive. So this is the same thing. So I would like you to consider to incorporate the stops for each trail. Okay, and the stop will store data to other stops. Okay, so it's almost like a binary tree, but except it's not a binary tree. Okay, so when we try to do a binary tree, right, each node has two children, right? Up to two children. Okay, so if you want to do the stops for trails, each stop can have multiple stops connected to it. It's like if I maybe draw the diagram for you, maybe that helps. This is some new idea, not new for us, or for most of you at least. Okay, let me share my screen. All right, so so I'm going to draw it here, right? So to review you, this is a binary tree, right? So each node has up to two children, correct? So that's why you can have a left child, right child, right? Because up to 2. So if this doesn't exist, that will be null. But otherwise, you have another node, correct? So now you have trails could be potentially like that, right? So you can have that. You can have that. You can have that, and you can have that. So potentially you can have you can see that's called a graph. So graph is a general case of a tree. Okay, it's a general case. The most important thing about a tree though is each node has only one parent, right? No matter how many children you have, each node only allowed to have one parent. That's the definition of a tree. Okay, so on my left, that's tree. Okay, but on the right is no longer the case because potentially you can have multiple ways. So potentially you can have something like this and this. So that's called a graph. Okay, so we are no longer saying a node has a certain number of parents or children. Instead, we just record every node. Okay, and then we have a linked list, and that linked list will contain the address for all the other nodes. So say this is my A node, right? This is my A node, and the A node contains a linked list. Okay, and linked list contains all the nodes that connecting to this node. You can say this, right? So you're gonna store all that. Okay, so now if you want to travel, say from here, okay, to here, that's the start, to here, that's the end, right? So potentially you have many ways to do it. See this? You can go this way, right? You can go this way, you can go back this way, and this way to do it, right? So you can have many ways. You can imagine that. You can have many ways to get to the same location. Okay, so basically you can present many unique combinations of segments. Okay, the path to reach the destination. Okay, can you see it? Can you see it? Right. So basically, you're gonna say, okay, I'm gonna start from here. This is my starting point, right? So I have a linked list that contains all the adjacent ones. This is 1, this is 2, this is node 3, this is node 4. So okay, the node S that has 4 nodes, right? Right. Then you go to the first one, and the first one say, oh, you have 3, right? So this is the 1. This is 2. This is 3. This one's the same one, so you got this discard of that. So this one you have 2. So now you're gonna have go into 2. Okay, and then when you finish it, when you go to the 2, then this gives you 1 route already, right? This to give you 1 already. Okay, then you go back. Don't forget this one had a 2, right? You're gonna back up here. You're gonna pop this one. This is a stack. So every time when you add a new node, you push that into a stack. So that's how you keep track which node is you're visiting, right? And then when you finish, you reach the end, right? You're gonna pop this. You're going back to this node, and now you're gonna go to the second node, which is this one. See, you're gonna go this one, and this one has a 1, 2, 3. Then you say, okay, I would go this one. See, because this one had this one had this one as well, right? So you have to go back to this one, see, and then go back to this one. So basically, you have to keep on adding, keep on popping, exhaust every single possibility. I don't know if this is a little bit more too complicated. I think if I made it easier, would it be less complicated? So you would just exhaust every single possibility. For example, right now I can probably do. So I will start from here. I'm gonna push this into my stack, right? This is gonna my stack, right? So this one, no problem. There's only one way to do. You go in here, You push this one in. Okay, you push this one. When you push this one, and then you look at the 3, right? This one, the one you visit, you don't want to do it again. So this one, this one, this one, right? And then this one, they give you the destination already. So that give you one path, correct? That's the first result. And then you pop this one, you back to here. Okay, when you pop to here, then this one is done last time. So you do, say, this time, you go this way. So you push this one in onto the stack. Then push this one on the stack, then you have 1, 2, 3, right? Then you out of the 3, you will push this one. Okay, you push this one. And this one, you have 1, 2, 3. Then you push this one. And this one has 1. So now you second time you get destination. When you get this destination, you pop that one again, you back to this one. Right, this is on the stack. This one is already visited, you pop that. There's no more out of here. You back to this one. But we just did this one, so we left this one left to do. Right? So we visit this one. We push this one on. And this one will give you 2 more. So you push this one on again, and this one goes to this one, and then this one do the same thing. So you just keep on pushing the pop. That's called a depth first. Depth first search. Okay, so you use a stack to help you to accomplish this. So if you are interested, take a look at the graph. I can also give you a lecture on that. Okay, another one is called breadth first. Breadth first is you starting from here. I go this one, this one, this one, this one. So put them into a queue. Okay, and then when you finish, then you go back to this one. You do this one, and there's no more. So you go this one. Then you go to the next one. Maybe that's the one. And then basically you use a queue to record which one you have visited. Okay, so this way you could produce all the possible paths from 2 points. Okay, and then of course, each segment you're going to add a, in addition to the location of the stop, also the distance between the 2 stops. Okay, so 3 miles, 3 miles, 4 miles, 6 miles. So this way, when you have a path, once you create a path, you can add the numbers together to give you the length of the trail of that path. Okay, so that is something called a graph. I thought it was interesting. If you have time, you should do this. That will be a good experience if you have time. All right, so that's just the optional piece, I guess. See if you want to do it, and if you're interested, we can have a lecture on that. It's actually very interesting. It's okay. So now we have the 3 data types to deal with, right? User profiles, trails, history. Okay, so I don't want you to develop a whole application yet. You just look at each data type, and then you say, okay, what am I going to do with this, right? I need to search, right? Because when you log in, you have to do search, correct? So always think about, do I need to do search? Yes. What I'm going to search by, right? I'm going to search by username, or I want a new thing called ID, because you can always incorporate the ID, a unique ID into your data structure, even though I didn't specify. Okay, so trail has ID, each trail has ID, and each user has an ID. Each history event has ID. Each event, each hike you did has ID. Okay, so we know how to create ID, right? When we did a person, like a student ID, and we know how to do those, make sure they are unique. So you just have to look at what kind of thing you want to do with the data type. You want to search, you want to log in, that means you want to search, correct? And you want to add as well, it means you want to insert, right? Because whenever a new user log in or sign up, you have to be able to add a user profile to the data structure, right? And you also want to be able to delete if somebody, not paying the subscription. So you want to prevent them from logging again. You can disable or delete that account, right? So those are things you say, okay, that's what I want to do. And then each of those, then you think about what's the best, fastest big O, right? One is, so that means that will require you to use a hash, right? If you want to get a one to do search, the only way to get a one to do search is a hash, right? The only way to do it is a hash. So now I did say that we don't know how many user profiles are going to be, right? We don't know how popular this application is, so we cannot really set a number when we create the application, right? We don't know how many users are going to be. So that basically eliminates the possibility of a hash for user profile. Do you understand? So there's no one. In other words, there's no big O of one. You can't really do it, okay? Because whenever you want a one, you need a hash. Hash needs an array, and we don't know the size of the array, so we cannot do it, right? So now you have to try something less efficient, and the next one would be login, correct? Right, login. Now login, you can think about, okay, if login, can I use array, a sorted array? Because login binary search, they'll give you login, right? If it's a sorted array, correct? So that's a possibility. So you write it down, okay, binary search is one possibility. And then you say, okay, is that really doable binary search? Because you think it requires an array, right? And I don't know the array size. So you say, oh, okay, that's not good. Even though binary search sounds great, gives me login, right? But still, I don't really know the size of the array because I don't know how many users are going to be there, right? So you say, okay, give up that idea. Then you say, oh, how about a tree, right? Because your tree, you do know, it gives you a big O of login, correct? As long as it's balanced, correct? Right? So now you say tree, okay. Then you think about, okay, tree. Then should I do, this is a tree set, right? Okay, a tree set that's, and then you have a tree map, right? You don't want to have a hash set or you don't want that, right? So you want to say, okay, a tree set or tree map. Both are using trees, correct? Tree set and the tree map. And none of those using hash, which is okay because we cannot really using hash, right? Right? We already gave up that idea. So now we have a choice of hash, tree set, and second choice is a tree map, right? Now, which one is better, right? So both are balanced tree, right? Both balanced tree. And the difference is a tree set will allow you to store one object at a time, right? But a tree map, though, will give you a key and a value. So you have to store a key and a value. Yes? Okay, so then you have to think about, okay, should I use a tree map? Tree map means you're going to have a key, right? And key has to be unique, obviously. Correct? Tree has to be unique. Then you say, hey, what about a username? So username sounds like a good idea to be used as a key, correct? Right? Then once you give the right key, and then I can bring the whole object of the user profile, and then which will contain the password. Then I can test everything else, right? I can get everything else. So that's a possibility, correct? And then that big O will be login. And then you say, what about just simply a tree set, okay, without a key? So in other words, every time a profile comes in, you will have a username, have a password, right? I don't want to separate the username as a key. Instead, I just pack everything into one object called a user object and put in the tree set. Okay, Of course, the tree set means every user profile has to be unique, right? Which is all right because each one has a different username anyway. You test about, make sure that's happening, right? And so that's fine. And also, you try to may want to create a user ID anyway. So each object will be different. Okay, definitely will be different. Okay, so tree set is another choice, right? Tree map is a choice. Tree set is a choice. Correct? Now the question becomes, which of the two should I use? Can you follow? Now you have to decide of the tree set, which requires no key, or tree map, which requires a key, a unique key, right? Which one to do to go? So that's why I said at this time I want you to have this idea in your mind, because I think it's going to help you tremendously down the road for the rest of your life, probably even. That is called evidence-based decision. Okay, I bolded those two words in the description. I try to draw your attention to that. I think that's the. I don't know if you are aware of this. There is a quite a distinct way of um, thinking between the East Coast and the West Coast. Okay, if you go to California, you go to the companies, bigger companies like Google, Facebook, Amazon. They are very big into evidence-based decisions. Okay, there is a woman. I think she was in charge of YouTube. Sandra, forgot. She got really high position, and she had a talk, and she was famous for this champagne, this idea of evidence-based decisions. So in workplace, right, whatever decision, there's always different opinions. Forget it, right? There's always different opinions. So the very important idea, very popular in the West Coast, California, those places. They believe everything has to be evidence based before you actually decide. You cannot just based on empirical data. You cannot just say this feels better, this looks better. You cannot do that. Okay, it has to be supported by actual data. Okay, so if you remember this, right, for the rest of your life, whenever there's an argument, right, with the coworkers or in your family, so to speak, you have to make this a way of thinking. Just say, okay, maybe you're right, maybe I'm right, maybe some other person, some other people are right, right? We have to prove it. You have to have a data to support it, right? So now, given the two choices, um, a tree set and tree map, right? So we can test it. We can test it. We can generate the data. How do we test, right? We can generate data. We can try these two different data structures, okay? Because they already have APIs, right? So we just write those utility, remember the utility programs like emit, emit profile, okay? Then the method will take in an argument, like a number, okay? So I can emit 1,000 profile, then just put an argument inside the method, right? I need 1,000 profile. I need a 10,000 profile. I need a million profile, 100,000, right? So you keep on increase the number of profiles, right? Just by putting a different argument into that emit method. Then we'll produce the profile. Then you put them into the two different data structures, and then you time them, and then you can decide afterwards which one is more efficient, right? Because now you have the data. You can show people, you can plot out data, you can show people this is why we choose this one. You see? So if you follow this, you always win the argument in the end because nobody can beat the data, right? So I think that's the big difference between the East Coast and the West Coast. East Coast is more old school, more old, like a based on make a decision based on experience, right? Because 2 years ago I did something and it was all right. I did this it worked out okay, right? I didn't feel like it was slow, no good, no good. Okay, that's more like East Coast old school, right? Like you see a doctor will give you a prescription based on how you feel and stuff like that. No, that's old school, right? So at least keep that in mind. There is such a thing called evidence-based decision making. Okay, I think that's very, very important. Very, very important. Okay, there are a few things in life I think are important. This is one of the few things. Okay, that's make you always win your argument anyway, right? That's something you want to try. So that's why I emphasize that. And even though I never did this before, but I emphasize that this time to help you make decisions. Okay, you see, I give you time also. I laid out how to create. You remember the second homework said allow you emit names, emit books and titles. Remember that? So give you create a utility, right? To allow you to create a data for whatever number of items, okay, easily. So you package that into a method. So whenever you need data, just use that. So this way you won't mess up your application later on because that is a utility program for testing purpose. Okay, so that's why I will ask you to put them into a utility class on the side rather than incorporate it into your true application. Because once you decided which one to use, then you don't need that utility anymore, right? Because those are not real user profiles, right? It's only for your testing purpose. You understand? That's why I want you to separate them. Okay, separate them. You understand? So that's something I want you to try it, right? To try it, and sometimes when you're looking for a job, when you say you apply to a school, look at a job, whatever, and people sometimes ask you, how do you make a decision? How do you do this? How to do that, right? And you can, if you mention decision making or database, data-driven decision making, you can already talk about it. Nobody can say that's bad, right? Because nobody can beat data. Okay, so that's something you should always keep in mind. When you don't really have an answer, right? You don't know which one is better, but now at least you can say, I don't know the answer, but this is what I'm gonna do. I truly believe in, say, decision data-driven. So I'm gonna test it. That's what I'm gonna do, and then I know for sure. Okay, so I think that's a good answer, right? Even you don't give a definite answer, but at least you give a direction what you should do to get an answer, to obtain an answer, right? So I think that's something I want you to try at least once this time. Okay, so this way you test it and then you convince yourself this one is better, so to pick the better one, either the set or the map. You understand? Okay. Now sometimes see, let's talk about the trail, right? The trail. The trail is the same thing, right? The trails. You need to store all the trails, correct? And again, I said I don't know how many trails because it depends, right? People may enter, many trails or just limited to 100. I don't know. Same thing with the history, right? You don't know. So that means you eliminate the possibility of a hash for the same reason, right? Correct? Right? You don't know. The application may be very popular, used in the world, right? And so maybe the hundreds of thousands of different or millions of trails could be entered. So you say, okay, since I don't really know, so I cannot really do a hash. So now you're left with again those two things, right? you're left with a tree set or a tree map, correct? You're left with two things. Now, if you want to use then you have to decide which one is better, right? Then you may want to test. Okay, and you can test it like the same way I talked about before. Okay, but this time you probably will have a better idea because last time when you did the user profile, you tested already. So you should have a fairly good idea which one may be better, right, of the two. And then you can still test it. Okay, if the result deviate from the first from the user profile test, then you have to ask yourself what happened, why it deviated, right? What is causing the deviation? Why this time the other one is more efficient? Okay, so again, you cannot rely on experience. You have to provide the data to test it, right? Okay. Now, once you decided, say you decide to have a tree set, right, rather than a tree map. Okay. Okay. So the big O is log n, right? Now, does that mean you're going to use that for everything? Okay, to search every single trail by length or by elevation, by the type. Do you mean you still want to use that for everything, or you want to break them down and have separate data structures to store the same data, same trails, right? You have a different data structure. One may be easier to use when you search by name, right? When you type a name, maybe you just have a data structure that stores all the names of the trails. So when you type one word, and then the word will be searched, find all the trails with the same, contains that word. So you may need another data structure, holds all the trail names. So this way, when people search by name, you can find all the corresponding trails that contain that word, right? And then what you return is, you're not going to return everything about the trail. Instead, just return the ID of the trail. Now, once you have the ID, you can go to the tree set to find everything else. So now you have two data structures. One is helping the main one. The small one that is there for fast searching by name on the side to get the name fast, not really get the name fast, get the IDs that contains the name, the IDs of the trails. And then once you have the IDs, then you can go to the tree set to find the appropriate trails. It's almost like an index. When you search by name, you get a bunch of indexes. Identify the trails that contains those words, the user type, right? Then once you have the indexes, then you can go to find the actual trails with all the other kinds of information, like length, like address, and all that kind of information. So again, you're gonna have to make decisions for every single type of a search. Is this fast enough as is? Do I need another data structure so this way I can get indices and then to help me identify groups of trails or not? Okay, so those are all the decisions you're going to make. Okay, again, how do you make decisions? You're going to have to test. That's the only way you know for sure. That's the only way, and nobody can tell you that's wrong. You can always win the argument. Okay, so it will take you little bit extra time, right? That's why this week I just say, try to figure this out and try not to develop an application. Try not shoot for a complete coherent application. Instead, try to think about it, test it, evaluate, and then, make decisions on data structures at this point. All right. And then if you do want to incorporate the the stops, intersections, right, to incorporate the graph idea. Then you need another data structure called a graph to store all the information about the trails. All right, so so that means you need another data structure. Okay, that's called a graph to store. You have to. It's almost like a very complicated tree. Okay, so every node contains data about all the other nodes connect to that node. So it all has to be stored. Okay, so only if you have time, you're interested. I think it's fascinating. I think that's about it. If you can do this one day, you go to an interview, people ask you to talk about it. I think you're gonna have a lot of things to talk about, right? Your decision-making process, why you choose this one. I think hacking is cool. I think these applications are pretty cool. Put on the resume, better than some dumb things like manage a college we did in 148. Don't you think? Right, that's kind of lame. Right, so this is the more interesting. Yeah, you can talk about the background, why you did this, and because of the pandemic and people are locked in at home. Now I thought it's a good idea to have an application for hiking. So because we want people want to get out, right? So that's a good story. You need a story, right? Good. All right, questions. Jario, I think you had a question.
Yes, Professor. So for the just to understand correctly, so each
Wait, hold
user.
on 1 second.
Okay.
I see you guys have the ear, like a earphone, headphone on. When I talk and when you ask questions, you get a lot of noise from my side because I didn't wear that. No? Okay,
No.
so it's okay then. Because I never asked, I don't know you. I thought you guys maybe just polite, not saying. Okay, go ahead.
So just to understand correctly, each user is gonna be able to create each trail that they want to from whichever location to whichever location. It's not like we're gonna be given a set of trails that each user is gonna pick and do, right? They're gonna be able to create their own. Is that what you're saying?
Right. That decision we have to make later, but right now we don't have to make that decision. Right. That's about actual implementation, where the data comes from.
Oh, okay.
Okay, that's the decision we have now. Right now, we just have to decide, given
Given
say
the.
multiple trails, what's
Mhm.
the best way to store data, and knowing the more to come, more trails to be added. Okay.
Okay. Got it.
Now
Mhm.
you can write a utility program that will create those trails and automatically feed into your program to test.
Okay.
And those
Okay.
are dummy trails, obviously, right? If you want to do graph, you also have to have methods that will produce stops on a trail and provides elevation at each stop, provide distance between stops, and then so on and so forth. So those are just the ways of generating data. So we don't have to make a decision yet.
Okay.
Mhm. All right. Anything else? You guys okay with it?
Yeah, sorry.
Right.
I
Okay.
just
Go
have
ahead.
to. I have to go, Professor. I'm sorry.
Okay, that's fine.
All right, take care.
Mhm.
So you're saying we need to have the stops and the
Well, you don't have to, Chris. You don't have to. It's like an optional thing. I think it will be interesting to do it. It's called a graph, and if we want to lecture, we can do a lecture on that. How to store data like that, like Google Map, for example. That's a graph, right? When you travel, you say, I want to go from here to Manhattan, and there are many different ways to get there, right? And then you may decide what's the best route. It could be based on the travel distance, based on the travel time, right? And also based on toll, right? Whether you have to pay toll or not, or based on congestion, okay, at that moment. So there's a different, or your commercial traffic, your commercial truck. So you cannot go to those certain state parks, right? You can only go on LIE. So there are different constraints. So that's a graph problem. So if you have a time, I think it would be fun to take a look at that data structure and then apply it. And then you don't have to make it complicated this time, because trails are not very complicated. They usually have a bunch of stops. They don't really have a lot of intersections. They don't have, at each intersection maybe there's a fork. You really have something more complicated than a fork.
Oh yeah,
right?
I remember the one time I went hiking upstate, and it was like all these different paths. I think one of them like ended up going into like another town or something.
Right.
Yeah.
Right. So it's interesting. I think it's an interesting project. Maybe just me. So I told you that just indulge me and try to do something. I'd be enjoying reading and watching. Okay. Anything else?
So just for the trails, when we're storing them, we're trying to find a data structure where we can store them. And when we're using them to try to connect. So like if you have like you're at location A, you'd use what trails to get to say location C or something like that? Or are we just saying these are the trails and we're going to add these to your history?
Right. So so if you don't want to graph, that means there are no stops. Okay, there are no stops. So we'll picture like this. I'm gonna clean this up. If you don't want, what I'm doing. If you don't want to do graphs, okay, and then you will be just like there's a trail. So this is not one trail, there's a trailhead, that's the address, and then there's a name called A, trail A, right? And there's another trail somewhere else, and you have the length, there's trail B, this is the address, there's the elevation gain, right? So that's pretty simple. And the name of the trail will be a bunch of words, so people can search. For example, I just remember the trail name has a pine in it, so when you type pine, then all the trails that contains the word pine will show up, allow you to choose, right? And then another one will, then you say pine barren, then, the trails without barren, but will show up, but only the pine barren will show up, right? So that's like a search problem, right? So basically just go through all the names and then, so you may want to store all the names into a separate data structure just for the sake of searching. Comprende? Okay, just for that purpose, in other words. So whenever you want people type a searching name, use that data structure. But every time when you add a new trail, though, the add method is not add data into one data structure anymore, because not only going to add that into the say a tree set, but also the name has to go to a separate data structure in case people will search it, right? So this time, every time you do an add, you have to say how many data structures are going to be affected. When you do a remove, you also have to decide how many data structures are going to be affected. So the add methods, remove methods are not going to be that simple anymore. You may have to involve a couple data structures. Comprende? Okay, I think it's an interesting project because also it's interesting because now you can be more creative, right? You can find things out yourself by testing things. And I think that's the ultimate skill you should have, right? Obviously, because eventually you're going to be all independent, working on your own projects. Yes, Leo.
So just to get clear, we're just testing right now for searching and inserting in to see which data structures works best with the data that we're given.
Right.
We're given, right?
Let me generalize a little bit, right? Any data structure, you have to think about a few things. One is when I add to it, how fast can I do? Right? And then that's one. And then secondly, if I want to remove, delete, how fast I can do. Third thing is if I want to insert, how fast I can do. Search, I mean, add is insert. Search, how fast I can do. Okay, sometimes there is a discrepancy. In other words, insert can be really fast, but search will be very slow or vice versa. So all the things, then you have to say, okay, do people do search more often or do insert more often? Right? Say trails, right? Say trails. I just tell you trails, or even user profile. You think about it. Every user will insert once. Every trail gets inserted once, right? Every user profile gets inserted once, correct? Once insert is there, it gets removed once also, right? Once removed, it's gone, correct? But that collection of trails will be searched all the time, correct? Every user will search, right? So you want search to be fast. Same thing when you log on. When you try to log in, the same user may log in many times. So the more user you have, the more login attempts you can do have. But insertion, deletion is going to be infrequent, not nearly as frequent, right? Only when you have a new user, you add once. When you quit, you delete once, right? But mostly will be searching and updating, right? Because whenever you finish a hike, that part has to be added to the history. Don't forget that. Add the history may not be bad if it's a linked list, right? You can add first because the list will keep the order, right? I mean, insert the first, insert last. Remember, it could be really big of one, so you don't care how big the history, how long the history is. Yes, you keep the order. So those things. But if something is too long, the linked list is too long, then you may say, oh, maybe that's too long. I want something that give me order, but will be faster. It still give me order, but faster. Okay, then you may have to think about another way. You can insert fast, because when you insert into a tree, you don't keep the order. Don't remember? A tree don't keep the order, right? You could be sorted, easily sorted, but it doesn't keep the order of insertion, right? But when you have a history, you don't want to be sorted. You don't want to be sorted by anything. You just want to see when you did which one at what time, right? One after another. So all the things.
Could you give things an ID when you create it and insert it into the tree, so it's being sorted by that key?
Yes, that's a possibility. Yes, that's a possibility, right? See, all these are possibilities. But how do you know which one's better? What do? You test it. That's the only way you know. So that's what we call evidence-based. Comprende? Anything else?
Just a idea for storing the user's logon information. Could you use a hash map?
Okay.
Hash is based on array, so that means that you're gonna have a limited amount of users. Isn't it better than a tree map?
We talk about, right? Because if you want to do a hash map, because the word of hash is based on a hash table, right? So we're going to review that if you don't remember. Hash table basically is an array, right? So that means you have to create an array first. And then if you don't know how many data items you're going to have, then it's hard to create an array with the right size. So there's a chance the array size is either too big or too small, right? If it's too big, you waste space. If the hash table is too small, then the array makes it really full. And then you have to create a bigger array and then rehash every single data item from the old hash table into the new hash table. Right? So that actually a very slow process, a very time-consuming process. Right? So you cannot even guess, say, how big it should be because you have no idea. Even the history, you have no idea. Right? You could be someone just did once. There's only one item in the history, but somebody may be crazy. They do every week or many times a week. So the history may be much longer. So you have no way of knowing how big the array should be. Right? So that's what the hash map should be. And so you don't know. You don't know. Okay. So I guess what I'm saying is, whatever decision you make, okay, you just have to be able to justify with the data. That's all. Because that's the only way you know is correct. You should not make a decision based on feelings. Jaleo, you okay?
Yeah, just the way you said it, based on feelings rather than data. I find it kind of funny.
It is, right. Right. So you have to base on cold data. And that's something takes some time to get used to. And I think it's a life strategy. Very useful, I think. You may want to keep that in mind, even when you're not doing computer science, right?
So
Because that's the best way to diffuse an argument, right? Otherwise, two people argue forever if you don't use data, right? You never get a conclusion. And you can stop the argument right away, just saying, okay, let's not argue it. Let's go get the data. Right? Then you stop the argument. Otherwise, it could be going on forever. Right? So you do need something that's there to serve as a judge, right? Serve as a criteria. So I think that would be something good.
so just to clarify what Jaleel was saying is we should just focus on like insert and search, or like
insert, search, and remove. That's basically what the structure is for, right? I mean, there's another one like update, but update basically is a search.
and so then that would tell us kind of about the performance.
Right,
so,
and then you have to, sometimes there's there is a deviation of the three. Like one data structure may be good at insertion, another one may be good at the searching. Then which one should you use? Right now you have a conflict.
But
right, then you have to see which ones used more often.
Yeah, and we're dealing with profiles like of users and also trails, but those are like the two main types of data, right? So then, so focus on all that, like for each and for each like type of data and which function you're doing.
Right, so and then probably for both, I would say search is more often used the function than insertion and deletion. I would say, right? Well, like when you create an email account, you create the email account once, then you have it, right? Then every time you use it, it's a search because you have to go through the data structure to find the match of the username and password. That's a search.
True.
You see that? So there's a lot more searching going on than insertion and deletion.
So consider that. Is that what you're saying? Like maybe it's okay if insert is not that great because you're not going to use it that often.
Right. Well, only when you have a conflict, competing data structures to use, then you have to factor that in, right? Because one data structure may be good at insertion, but bad at searching. But now you say, hey, searching actually happens more often, so I want to give a little bit more weight onto searching.
Right.
So I would lean towards a data structure that's better at, searching. Right.
Make that the important thing.
Right. It is important, right? If you think about it, right?
decision making. Yeah.
Right. So this is something I want you to try it once.
Okay.
Hopefully you will see the value of it, and then in the future you're gonna have make a lot of decisions anyway, so this will be something you can use to guide yourself when you make a decision, rather than you're based on experience and the feelings. Yeah, this happens in every area. You might think this happens in computer science only, because that's people in computer science say this is a lot. Data driven, okay, evidence based. But in other areas, that's also equally important. Okay, in medicine, when you diagnose patients and all that, that's equally important. Okay, so that's what I want you to give it a try, and hopefully will convince you that that's something you can use in the future and help you, down the road whenever you have decision to make. Okay, so no rush to implement the application. No GUI needed. Just decide on data structures for now. And then if you could finish this by Wednesday, if you need more time, we can give you a little bit more time, but at least try to work on it, okay, for your own sake. And then we can add to this, and then we can develop this into a full application later on. Okay, once we made data structure is the most important one, right? Once you decide that, it's just a matter of implementation with the GUI and stuff. Another thing I just want to mention, I think I mentioned in the description, is use APIs, right? If you want to sort, you can use API. If you want to use tree set, use API, or tree map, use whatever, use API. Don't try to implement yourself. Okay, so this way your code will be much more concise. Okay, will take much less time to implement. Understand? Yeah. So I hope this exercise will make you think more about data structures, because it's in a way is open-ended problem. Okay, and you have to decide on your own. All right, and give you a little bit of extra work if you are interested in doing. That's a graph. All right. If there's enough people who want to do it, then I may just give a lecture on graph, and, if you're interested. Okay, any other things you want to ask? No? You guys okay? You guys, right? Okay, and also I think you should, if you haven't yet, you should have your GitHub set up. Okay, if you have GitHub set up, then as you try things, as you write the code, you can upload everything to the GitHub. So keep a history there. Okay, if you all have it, then I don't have to talk about it. Otherwise, that's my topic on Wednesday, how to set a GitHub. So this way you can keep track of everything. Okay, but if you're already doing it, you have no problems, then we don't have to do it on Wednesday. Is it okay? Are you guys starting using it, or you guys not using it? And then another thing I want to talk about is a UML diagram. I mentioned it briefly. Remember when I showed you the collections framework diagram? Remember, it has like a solid line with a triangle, and then some is called implementation. That's a dashed line, and then extend. That's like a when you use they call generalization. That's like a superclass, and that is a that is a solid line with a empty triangle pointing to the superclass or super interface. So a rectangle would be a class, but sometimes you may have something called a stereotype that we specify that could be an interface or something. Okay, so that's a very important, actually it's important language. It's called the modeling language, UML, Universal Modeling Language. So we're going to talk about that at some point. So that also is important. So you don't have to write a code. You can already express yourself how to design your program. Bueno. Okay, so I guess I will just quickly review with you certain data types. I think the last time we talked about linked list, right? We talked about all the linked lists, and we use linked list for priority queue and for queue and for stack as well. Don't forget, a linked list can be used for stack, a queue, and a priority queue. Okay, although Java provides a stack API, but you don't have to use it because the linked list can do it as well. Okay, basically just want to access from one side of data structure, right? Because use a push and pop, right? So then just quickly, we're gonna go over binary search tree, right? I think we went over most of it already. So basically, you just have a root node, right? A root node. Then you can have up to 2 children. If you are not limiting to 2 children, that's just the tree. So you could have something that's a tree. Okay. You don't limit to 2. That's a tree. But if you limit just up to 2 children, then that's a binary tree. So that will be a binary tree. That's where the binary comes from, up to 2. Bi is 2, right? And then if you have the left child smaller than the parent, and the right child is equal to or greater than the parent, then we call that binary tree a binary search tree. Okay, so there's a difference between a general tree, which has an unlimited number of children, right? Okay, first of all, it's a tree. Tree means the node cannot have more than one parent. Okay, if you allow more than one parent, then that's a graph. Okay, so a tree is a special case of a graph, right? Now within the tree, you have if one parent can have up to 2 children, then that is called a binary tree. Okay, anything other than that is called a tree. It's just a tree. Okay, a binary tree is a special case of a tree, obviously, right? Okay, now within binary tree, if the left child is smaller than the parent and the right child is greater or equal to the parent, then that's a binary search tree. So now you have the word search in there, because that tree is very good at searching. Okay, now once you have a binary search tree, you have to be careful, because to get all the benefits of a binary search tree, like a big O for log n, right? The tree needs to be balanced. The tree needs to be balanced. Okay. Now, what is balanced? The balance of the tree means the left subtree compared to the right subtree, the difference of the 2 subtrees are not more than 1. 1 is okay. 2 is no good. The difference is 1 level difference is fine. Okay. The number of levels of left subtree and the right subtree cannot be more than 1. Okay. So for example, right now that is a balanced tree, right? Binary search tree. So this is also balanced as well, because on the left side you have this many, on the right side you have 3, on the left you have 4. So that's still balanced. Even if you look at this subtree, the right side is 2, 1, 2. The left side is 1, 2, 3. So that's still balanced. Okay. Now, if you have something like this, that's also balanced, right? If you have something like that, that's still balanced. Because if you look at this side, this is the 2, this one is only 1. So if you look at this part, the right side has 2, the left side is only 1. So you don't have this one missing. So the difference is 1. Okay, it's okay. Or less than 1 is 0, that's okay. But the levels are more than 1, it's not good. Now, for example, if you have something like this, that's no longer balanced. Because on this side, you say you look at this side, this is 1, 2, 3, 4. So left side you have 4 levels, right? And on this side though, you see you're missing this one. Okay, so this side you only have 1, 2. Okay, so this side you don't have 4. So difference is more than. So you need 2 more to get to the side, to the same length as this one, right? So that is unbalanced. Something like this is unbalanced. The level difference is more than 1. That means it's unbalanced. Okay, so then we have many different ways to balance a tree. Okay, the most common one is called a red, black tree, RB tree. Often people just call RB, red, black tree. And then there's 4 rules we have to obey. Okay, when each node has to have a color, right? You remember that? And also the root has to be black, right? And then the black depth has to be the same. So from the root to every single node of the tree, okay, the number of blacks have to be the same. Okay, and another one is a red node cannot have a red children, cannot have a red child even. A red node cannot have a red child, but a black node can have a red child and a black child. Okay, now so if a tree is not balanced, there are 2 things you can do to balance it. Does anyone remember of the 2 things you can do to balance a tree? There are 2 things total you can do to balance a tree that's not balanced. Anyone remember? The first thing is you can change the color of the nodes. Okay, you can change the color, and but changing color itself is not going to balance the tree. Okay, if it's unbalanced, that's because the difference in levels is not difference in colors. So by changing the color itself alone is not going to be able to balance your tree. Can you see that? If a tree is not balanced by playing different colors, it's not going to balance it, because balance or balance is defined by a number of levels. It's not by number of color or the colors, right? So the real thing you can do to balance a tree is by rotation. Okay, you have something called left rotate, something called right rotate. Do you remember that? Left rotation, right rotation. So rotation is actually the ultimate tool you can use to balance a tree. Okay, so in order to get that kind of efficiency, you have to make sure the tree is balanced. Bueno. Okay, so all the tree set or the tree map, whenever tree in API is always balanced. So you don't have to worry about the problem. Okay, so essentially when you try to use a tree, if you use API, it's always guaranteed to be balanced. So there's no need for you to worry about balancing. That's why we didn't really implement how to balance a red-black tree, okay, because nobody does it. It's kind of complicated to do. could be complicated. So, but you do have to remember how to those APIs, okay, to use them. That's about it. Okay, so the reason the binary search tree is efficient is because, first of all, insertion, deletion, okay, search, all three common used things are log n, big O of log n. Okay, so that's pretty good, right? If you want to insert is log n, you want to delete is log n. If you want to search something, it's also log n. So you don't have to sacrifice one for the other. Okay, nobody gives you one. So you can forget about that. All right. So so that is binary search tree. All right. So another data structure is hash table, right? The hash table is where the word hash set, hash map comes from. Okay, hash. Okay, hash is based on array. So you have an array. You have to have an array first. Okay, you have to have the array first. That's the key, right? Whenever you want to do a hash table, you have to have an array first. Good. All right. So then when you try to store data, it could be number, right? It could be number. Say I want to store 10, 5, 200, or 1,000, whatever number you want to store, right? Those numbers have to be hashed, going through a hash function. So all the number has to go through f, okay, hash function. And the hash function will turn the original values into another integer value. And that integer value is going to be used as an index, okay, in the array for you to store that piece of data. So for example, if 1,000 comes with a, after the hash function comes out with a 5, for example, then location 5 will store 1,000. Okay, and 10, once you go through the hash function, comes out value of 2, then 10 will be stored at location 2. Okay, so in other words, the index where the data is stored is based on the data itself. Okay, it's based on the data itself. Okay, so that's just the case of if you try to do integers, right? And you can do this for anything and everything. Okay, you just have the right hash function. So you can do string like words, right? It says string 1, and it goes through a hash function, and will give you an integer. Okay, integer 1. And there's a string 2, and it goes through a hash function that will give you an integer 2. And a string 3 goes through a hash function if you go to integer 3. So all those values, it will go to the right location by using the integer as the index of the array and store the data right there. Okay, right? So now if you want to look for string 3, okay, so you want to look at string 3 is a hello, right? So I do take the hello, I go through the same hash function. Okay, that will give me integer 3, right? Still the same. So I go to integer 3, say this is my integer 3, that's like a 10, say. I just see if hello is there or not. If it's there, that means, hey, there is a hello. I found it. If there's no hello, then they say there's no hello. The hello is not stored in there. Can you see the point? Okay, so similarly, if you have a profile, right? Say you have a user profile, right? So this is profile 1. I go through the hash function, and I get the index, say this. I'm going to clean this up. Profile 1 is stored at location, say 3. And the profile 2 goes through the hash function, we'll get location 5. Profile 3 goes through the hash function, we'll get the location 1. Say, right? You get the index. Okay, by the way, 351 is called hash values. The function is called a hash function. Okay, now that means P1 is going to store at 0, 1, 2, 3. So that at location 3, 0, the index 3, P1 is going to be stored there. Okay, now P2 will be stored at location 5. So that's a P2. That's 5. This is 4, right? And P3 will be location 1. That's a P3. Okay, so now if you log in, if you try to log in, oops. Okay, now if you try to log in and then say this is username, if I found out the username, and I can go username, or I say this is username, right? So I username, I get a function that's a 3. So I go to 3 and see if that username is there or not. If it's there, that means okay, I found the username. Okay, so if it's the object stored there, then I would find the object. But if it's not, then you're gonna have a way to find the object. If you just store the username, you're not gonna give you. This will find the username fast. Will not get the password easily because these are strings, right? If you use the strings to do it. Okay, so those are all things you can have to consider. Okay, so you can see that you have to have a array first, and the array, because you need an array, so you need to know how big the size has to be. You okay? So anything with the word hash, you need an array, and that means you need to know the size of the array. And if you don't know the size of the array, then you can forget about hash. Like a dictionary is a good example. You can use a hash map because the dictionary, you know how many words in the dictionary. In other words, you know how big the array should be, right? So that's fine. That's why when you do spell check, it goes so fast because you know how many words there total. So you can create array size that to accommodate that. And the load factor is preferably under 0.5. Okay, that means the data items should take a half or less spaces in the array. Because one is getting full or getting too full, and then the hashing, the searching gets slower. Okay, there's other things we talk about collision, and then the ways to avoid collision or resolve collision. I don't know if you remember, right? One's called linear probing. Is to try to find the next location, see if it's available. If it is available, you store your data there. The next available cell, that's called linear hashing. And there's another one called quadratic hashing. Probing. Linear probing and quadratic probing. Okay, and then there's a third one called double hashing. Use another hash function to jump to a place step number of cells away based on the data, called double hashing. And then there's a whole total different approach. So to avoid the collision, to resolve collision, is by using something called, what is it called? Another solution, separate chaining. So basically what you have is array. Each array just rather than contains the data directly, it contains a data structure, either a tree or a linked list. So whenever you have a collision, just add that to the linked list, right? So if there's only one item, you just put a one link. If it's a collision, that means you have two. Then you have to insert one. So that's called a separated chaining. And in this case, load factor doesn't matter now, as long as the array size is big enough. In this case. So that is hash map. So you just have to make sure hash table. I mean, and then the applications will hash table in API and the hash map, hash set. All those are based on this concept, hash table concept. I think we covered all the data structure stuff, reviewed all the stuff. I don't really have anything to add. The only thing we didn't cover, or didn't review, I mean, was all the sorting algorithms, like a merge sort, remember? And shell sort, quick sort, radix sort, heap sort. So we didn't really review those. If you feel you would like me to review, I could have another day just review all the algorithms. Okay. Now, if you want to use the algorithms, you can use the arrays class. Remember the arrays class? Another one is called collections class. Collections class, and then dot sort, dot parallel sort. Remember that? Dot search, dot binary search. So those algorithms that are integrated into the collections class as static methods, or in the arrays class as static methods as well. So I think that's everything. And I think finally we put a closure, hopefully, on the data structure course we took last semester, or in the summer. Summer was even worse because it was so time pressed. All right, so what do you think? Can we move on now, or do you need to review the sorting algorithms? If you don't need, we can just move on with the new stuff. And now attention needs to be, I think we have a good foundation. If you understood everything I talked about up to this point this semester, you should have a decent foundation to work on the project. For this part, at least, this leg of it. Okay. You all right? Mm-hmm. Any questions? Don't think one set of data, like a profiles, has to be only in one data structure, okay? Based on the purpose, you can have multiple data structures. But you just have to make sure, whenever you update an item or insert item or delete item, all the relevant, related, associated structures are going to be updated as well, right? So now you can extensively use some kind of ID, okay? Because ID is serve as an index to link different data structures. In other words, say if I have different data structures, is one, another one, and then if you have an ID, the ID can be referenced among different data structures. As long as you return the ID, then you can jump to a separate data structure. So the ID serves as a bridge between data structures. The ID has to be unique. Can you see that? You don't want every data structure to drag all the data of that item, like a trail. You don't want every data structure holding everything about the trail. That's too much. Okay, just hold one, that's the ID. Because once you have an ID, you can use the ID to go to another data structure to get everything else. Right, so that's like a bridge, that's like an index. And this serves the foundation for databases. We're going to talk about later on in the data structure, in the course. Databases, that's ready-made databases for storing data. It's like specifically made for storing data. So, okay. Now each data structure should be as simple as possible. So be faster. Don't drag a big tail. Avoid that as much as possible. Multiple districts is fine. Just use the most efficient one. Okay, and test everything when you make a decision. And this way you will never get it wrong, because now you have data supporting your decision. Bueno, anything else? Hopefully you can get on to the project, and then if you could test everything out, make decisions, then maybe next week we can start to implement it. All right. Okay, good. All right, adios.
All right, thanks.
Bye.
Thank you.
Bye.